In the GitHub repo for our entity component system samples, you will find a lot of DOTS learning material, including the main physics samples project, but also this introductory material that includes a smaller sample project called Unity Physics 101 and this accompanying document. In it, we start with an overview of just what are physics engines about, what can they do, and then it covers the essentials of the Unity Physics API, and then it ends with a walkthrough of the samples in the Unity Physics 101 project. If you want to understand Unity Physics and these samples, I recommend giving this a read-through, but for the sake of a quicker, even easier intro, I want to walk through these samples one by one in this video. So looking first at this sample called Pachinko, we have these pegs, these blue pegs, and the gray board behind them. Those are static colliders, and all the yellow balls are dynamic rigid bodies. And if I pause here and go look in the entity inspector, we can look at what a peg, a static collider, looks like. It has standard transform components, rendering components, and then for physics, it has two things. It has the physics collider component and physics world index. The idea of physics worlds, the idea is that within a single entity world, you might sometimes want to have static colliders and physics bodies, dynamic rigid bodies, that are simulated entirely independently. And so you can control which logical physics world the physics entities belong to by setting this value. By default, the value is going to be 0. So by default, when you create physics bodies, they belong to the default physics world. But in some scenarios, maybe you would want a second physics world, which would have, well, it doesn't really matter what the index value is as long as it's something other than 0, but generally you would make it value 1, right? Anyway, there are some niche scenarios where that kind of physics simulation separation is useful. In most cases, though, probably you will just have everything in the default physics world. Okay, so the physics collider now, this of course represents the collider geometry of the object. And by virtue of having this component, that's what makes it a collider recognized by the physics systems. And you can see in this case for the peg, we have a capsule collider shape. In some scenarios, you don't necessarily want every collider to collide with every other collider. And so you can control this with the collision filter, as we'll see in a later sample. This material for the collider has a few properties, including friction and restitution, which is a fancy word for bounciness. And then under mass properties here, you have this mass distribution, which defines a center of mass, and also this inertia tensor, which basically describes how the body reacts to rotational forces when they're applied, how it spins around its center of mass. And then if we look at one of the spheres, what we have in addition to physics collider and physics world index is we also now have physics damping, physics mass, and physics velocity. Damping describes how the velocity of the body degrades over time. It diminishes. In this case, though, the damping values are both set to 0 for linear and angular. So actually, if this component were removed, then it would be treated as if the damping values were 0 anyway, so we don't strictly need it here. The mass component, of course, specifies a value for the mass, but it also has a center of mass value and an inertia, which is a bit funny because we have that as well on the collider, remember. There are some reasons for this redundancy, but in short, when physics mass is present, its value effectively overrides what's specified on the collider. And then lastly, we have the physics velocity component, which describes the current linear and angular velocity of the body. Now, if we look back at the regular hierarchy, we can see how the scene is set up in the editor. We have this subscene that contains, say, the surface and the spheres and all of the pegs. And if we look, say, at this one sphere and look at the game object that gets baked, what we have is we have the stock game object physics components, the PhysX engine components, in this case, sphere collider and rigid body. And what happens then in baking is that by virtue of having these game object components, what we get in baking, as the entity baking preview shows us, is we end up with the entity physics components we just saw. Now, understand that these game object components were, of course, created long before Unity physics even existed. So there are some cases where the naming of the properties here doesn't 100% exactly line up directly with what you get in the corresponding entity components. And so how these options correlate exactly to what you get in the baked entity can be a little confusing in some cases. These discrepancies, these mismatches, or just the unintuitiveness of how they map is something that the physics team definitely wants to improve in the future as game object physics and entity physics ultimately converge at some point in the future. But in the meantime, keep in mind there's some cases that are a bit confusing. Looking now at this variant of the Pachinko sample, this Pachinko compound colliders, these spheres now, the balls have these extra pink boxes floating around them, which are part of their colliders. So here, if I play the sample, you will see that each sphere, each ball with its pink boxes effectively act as if they're one rigid body, even though they're made up of separate shapes. Now, if we look at the runtime entities, what we have for each one of the spheres and its boxes is you have the sphere itself is this entity called compound that is a dynamic physics body. It has velocity, mass, damping, world index, and a collider. But that collider is, notice the type compound. It is a composite of multiple pieces of geometry. And that geometry is defined, as you can see here, as an array of children. There's the boxes, and I'm guessing the last one here. Nope. One of these is a sphere. But be clear, this is just invisible collision geometry. The actual rendered pink box that we're seeing, that is a separate entity. And so here for each compound sphere, we have its 4 children, these cube entities. And if we look at them, we see that they have this parent component because they are parented to the sphere. And so in the transform systems, the cube transform is updated relative to its parent. But notice that they have rendering components, but no physics components. These child entities, these pink boxes, at runtime, they're not physics objects at all. They're just rendered entities. If we look, though, at the compound prefab itself, the original prefab before baking, what we have is the root game object has a sphere collider, as expected. It has the rigid body component. But then the child cubes, they actually have their own collider components. They're not their own rigid bodies, be clear. They're just colliders. But what happens in the baking process is that the child colliders get, in a sense, hoisted up to the parent entity, the ancestor entity, which is the actual rigid body. So actually, as an experiment here, let's see what happens if I add rigid body to one of these children. What are we going to get? As you can see, that one child entity is now its own separate rigid body and not part of the compound collider at all, and so it just flies off independently. We have one more variant of the Pachinko sample called Pachinko collision filter. And here now we have red and yellow balls, which notice do not actually collide with each other. They just phase through each other. The way this is arranged is through collision filtering. The red balls filter out collisions with the yellow balls and vice versa. If I look here at the red sphere prefab, the red sphere is added to this layer called red, a custom layer that I defined. And if we look at its collider, you can see under exclude layers, it has the yellow layer excluded. I could select multiple layers if I wanted, but in this case, we just want to exclude with yellow. If we look at the yellow sphere, of course, belongs to the yellow layer, and under its exclude layers property, it says red. Now, actually, we don't really need the filtering to go both ways. If I disable the filtering on the yellow sphere now, and play again, you can see that they still don't collide with each other. Keep in mind that you can exclude multiple layers, so I'll not just re-enable red on the yellow balls, but also other yellow balls. So now what we'll see is that the yellow balls will fade through each other as well, not just through the red balls. In the next sample, called Gravity Well, we have these 2 orbiting red spheres, the gravity wells, and then the other spheres, the white spheres, they gravitate towards these 2 positions. There's a force being applied in our code every physics update that moves them towards the 2 gravity wells. So looking at the code for the sample, the main interesting thing is this gravity well system. And in it, first thing we're doing every update is we are moving the gravity wells. Understand the wells themselves are not actually physics objects. They're just rendered objects that we're moving in our code here. So that's not really interesting from a physics perspective. But the part that is interesting to physics is here where we are querying for all the dynamic bodies, all the entities that have physics velocity, a collider, mass, and a transform. And we are applying through this helper method of the velocity component, we are applying an explosion force. And that's how we are gravitating them towards the two wells. Notice there's this inner loop here for the two wells, so that we're applying two forces on each sphere, two explosion forces. Looking at this method here, it takes a lot of arguments. First, you pass in the mass of the sphere, its collider, its current position, its rotation, then the strength of the explosion here, which we make negative because we want it to be actually an implosion, not really an explosion. We want the balls to move in towards the gravity wells, not outwards. We also provide the position where the explosion originates, which in this case is the well transform position. And then we specify the radius of the explosion. Normally with explosions or implosions, you would have a non-zero radius, which effectively means there's a cutoff of how far the explosion reaches. And also effectively means there's like a fall-off effect, so that the further towards the edge of the radius, the lesser the force. So, things closer to the origin of the explosion should have a larger force applied. But in this case, we just made it 0, which effectively makes the radius infinite. And so there actually is no fall-off to the effect, which arguably isn't really proper here because it's, gravity, of course, gets stronger with distance. So it's not exactly accurate, I suppose, but good enough for our purposes. And then you provide also here the time step. And then this last argument is a vector that is supposed to specify the upwards direction, which for our purposes, we just make up. In the next example, laser sight, this is a demonstration of using a raycast. We have this character who moves around with a laser sight emitting from them. And based on the detected raycast to the nearest wall, we are modifying the length of the laser. The main piece of code for this sample is this laser system. And in its update, we are first moving the player here. And the way we do that is just through very ordinary logic, having nothing to do with physics. And then we have the logic here where we're doing a raycast to determine the laser length. And the way we do a raycast is first we have to get the collision world by first accessing this singleton called the physics world singleton, and from it, its property, the collision world. And then what we're going to do with this collision world is we're going to call cast ray to perform a raycast. And the first argument to the cast ray is this raycast input struct, which includes a start and end position, which effectively denotes the source of the raycast, where it originates, and what direction it travels in, and how far it's going to potentially travel. How far is it going to collide with things? For simplicity in the sample, we make the laser just always point in the same direction of the z-axis. So here for the endpoint, we take the player position, the same as the start, and add the max laser length on the z-axis. And then the last field of the struct is this filter, which we set to the default collision filter. Make sure you don't forget this, because otherwise our raycast won't match anything. The filter value will default to actually 0, not default, confusingly, and so our raycast would never match anything. So that sets up our raycast, which is then actually performed by this cast ray call. If the raycast doesn't hit anything, cast ray returns false, otherwise it returns true, and the information about the hit is set to this outvar closest hit. So in the case of a collision, when the laser hits a wall, we then want to set the laser length to the distance from the player to the closest hit position. Otherwise, if there is no hit, then we just set the laser length to the max laser length. Anyway, now we have the length of our laser. And last thing we do here is we set the endpoints of the actual rendered laser, the line renderer, which is not a physics-specific thing. But real quickly going through this, in the player component here, we have this Unity object ref that references the line renderer, and we need to initialize that if it hasn't already been initialized. So we find it from a game object, then set it on the player component. And then here's where we're setting the actual points on the line renderer. We set position 0 to be the position of the player, and position 1 to be the end point of the laser. In this next sample called elevator, we have this elevator platform that moves up and down. And notice that these other rigid bodies, they collide with the elevator as it moves, but the elevator itself does not respond to collisions with any rigid bodies, or in fact, it's collisions with the static colliders around the edges, the glass panels and the side pillars. And that's because this elevator platform is a so-called kinematic rigid body. It's a rigid body that has an infinite mass and inertia, and so the physics engine will not automatically modify the velocity of the kinematic itself. The kinematic velocity is only modified when you do so in your own code. And so, in fact, when we look at the code for this, what we see in this elevator system is all we are doing to get the elevator moving is we just have this logic that says, well, if you're not moving, then we'll make you start moving up, setting your linear velocity to the elevator speed in an upwards direction on the y-axis. And then if you are going up, when you hit the top, then we want you to reverse. And if you're going down and you hit the bottom, then we want you to go up. So that's the only logic here to make the elevator move along its path. All we're doing is setting the linear velocity, and the physics engine itself is actually moving the elevator, the kinematic. But again, the elevator itself is not in any way automatically responding to the collisions. The setup for this in the scene is very simple. The way you make a kinematic is very simple. Just on the rigid body component, you check is kinematic. And then if we look at the preview for the physics mass, you can see that the mass and inertia are 0. Whereas if I uncheck, they wouldn't be 0. In this sample called breaking bricks, these bricks here all have a hit point value. And when they get struck by a ball, the impact decrements the hit points. And when the hit points falls below 0, the brick gets destroyed. And you can see that the color of the brick reflects its current hit points, where full green is full health and full red is 0 points. Now, one thing we'll need to do in this sample is detect when the balls strike the bricks and determine what the force of the impact is. And the simplest way to do those things is by reading the collision events that are generated by the physics engine. However, these collision events are not automatically generated for all collisions. We need to enable them for specific colliders. And so here for the brick, on the box collider, we need to check this provide contacts. And that is what will enable the collision events for when the bricks collide with things. We could also enable this on the balls, but we don't need to. As long as one of the two things involved in the collisions we care about has this enabled, then we're good. For the code, all the interesting stuff is in this brick system. And notice that we are putting it in the after physics system group because we want the system to update after each update of the physics. And the first thing we're doing in the update is we spawn the bricks if they haven't spawned already. Here's where they get instantiated, and here's where we are setting their initial colors to the full hit points color value and setting their position to a random position. Next, to read the collision events, we need to access this simulation singleton and get it as a so-called simulation. So we get back the simulation object. Before, though, we access the collision events on the main thread, we have to make sure that any jobs that might still be running get completed. And then because we want to get details of the collision events, we need this other thing called the physics world, which we get from the physics world singleton. As I described earlier, there's this concept in Unity physics of separate physics worlds that have their own separate sets of colliders and bodies. So that's what the physics world represents. It represents all the colliders and dynamic things within that world. Now here's the code where we are looping over all of the collision events that have been generated in the last physics update. And then in this logic here, what we do is we take from the collision event, we take the two entities involved, entity A and entity B, and we do these component tests to determine which is the brick and which is the ball, and assign them accordingly to these two entity references. Notice we have to account for the case where maybe the brick is A and the ball is B, or vice versa. So that's why we have these two branches. And then for all other cases of collisions, we might have, say, collisions between bricks and other bricks or balls and other balls. We don't care about those, so here we're just continuing for those cases. Note this comment here that for a given collision between a pair of bodies, you get one collision event, not two, but you don't have any guarantee about which is going to be which. So it's kind of arbitrary which is going to be entity A and which is going to be entity B. So you have to test for both possibilities. Anyway, now continuing for the case where we have a collision between a brick and a ball, we call this calculate details to get more details about the collision, which includes this estimated impulse. Because here, when we decrement the hit points of the brick, we do so based on the force of the impact. The greater the impact, the more hit points get deducted. But then for cases where the impulse is below this certain minimum threshold, which I set up here to 2f, sort of just an arbitrary value, we actually just want to ignore the impact. And that's actually because when the balls come to a rest on the brick, when they sit there, that still generates collision events. In these collision events generated by Unity physics, understand in this collision events array, there's no distinction between newly contacting pairs of bodies and bodies that are continuing to contact from some prior update. So this logic here is effectively filtering out the case of the ball remaining in contact, resting on top of the brick. And then after reducing the hit points, we test to see if the hit points are now less than or equal to 0. And if so, we destroy the brick. Otherwise, we update the color of the brick to reflect its new hit point value. Last thing, when we destroy the brick, we don't do so immediately with the entity manager. Instead, we're recording the command into an entity command buffer. And then at the end, we're doing the playback of the ECB, which does the actual destruction of the bricks. In this next sample called activation plates, I have this character I can move around, and I have these trigger zones I can activate when I enter them. And when I do so, it'll spawn a little box. But as the labels indicate, these triggers have different logic. The one on the left here, the one-time trigger, I enter it, and it'll trigger the one time, but then if I leave and re-enter, it won't trigger again. Whereas the second one, the continuous trigger, when I enter, it'll keep spawning boxes on a timer. And the one over here, the re-enterable trigger, I can enter, exit, and re-enter, and it'll spawn again. And then finally, the one on the right here, it doesn't trigger when I enter, but it triggers when I exit, every time I exit the box. Okay. So if we look at one of these triggers, what we have is it has a collider component, but no rigid body. And so normally that would make it a static collider. And in a sense, it is a static collider, except by virtue of having is trigger here selected, that means that dynamic bodies like my player will not collide with this thing. They will phase through it. And when things intersect the trigger zone, it'll fire trigger events. Notice the trigger also has this zone authoring component that specifies a type. In this case, this is the one-time trigger. If we go look at the code, so in the zone component, we have the zone type, also a state, which indicates the current intersection state. If the player is inside, outside, entering, as in going from outside to inside, or exiting, as in going from inside to outside. The zone component also has these other two fields here that we'll explain when we look at the activation system, which is the code responsible for reading these trigger events and responding accordingly. So what we do in this system is we have here the code that gets the trigger events themselves. And just like with the collision events, we do so by getting the simulation singleton, calling as simulation, making sure to complete any jobs that might still be in flight so that we can safely access the events here on the main thread. Here is where we loop over the trigger events. And you can see this logic here, which is basically the same as what we did for the collision events in the breaking bricks sample. We're testing the components of entities A and B and determining which is the player, which is the zone. And then here for the zone, we are updating this physics update count, which is a counter in the system that increments every update of the system. This will be significant in our logic later. And then also for each trigger event, we are setting the zone state to either inside or enter. For the case where the zone was prior in the enter state, it now should be inside. And for the case where it was either exit or outside in the prior update, now it should be enter. For the case where the zone is already in the inside state, we don't need to modify the value. Now, for the case of the zones that in this frame aren't triggering an event, we have to do another loop over the zones. And in the case where the last physics update count is the update count of the current frame, well, that must be a zone that we just saw in this loop up here. So we've already set its state to either inside or enter. So we skip those cases. Otherwise, this test here tells us if in the prior update, this zone triggered an event. If that's the case, the zone is transitioning from inside to outside. And so we set its state to exit. Otherwise, we set its state to outside. In the next section here, we're setting the colors of the zones. For zones that are newly entered, we set them to the active color. And for zones that are exited, we set them to the inactive color. Finally, this last section is for the actual trigger logic. We once again loop over all the zones, get the type and the zone state. And for the case of a one-time trigger that we are entering, well, in the case that it hasn't already been entered before, because the last trigger time is still 0, then we spawn a box and we set the last trigger time so it'll be something non-zero now and won't trigger again. For the case of a continuous trigger that is inside, then we want to, based on this timer, we want to spawn a box when the timer expires. And when it does expire, this line effectively resets the trigger. And then for the other two cases, a re-enterable zone that's being entered, that's when we spawn a box, and on-exit zone that's being exited, that's when we spawn a box. Finally, last thing, if spawn box is true, we spawn an actual box. Now, an important caveat about this logic is that the way we're tracking the enter and exit state assumes there's only one thing, one player setting off the trigger. If though you had multiple players or multiple separate things that might possibly set off the trigger, then this logic would break down because it doesn't distinguish between different things intersecting the trigger zone. If we wanted to properly track the trigger state for multiple things that might intersect the trigger, then each trigger would have to keep a list, a buffer, that tracks the individual entities that might intersect with it. And only then could we correctly track the enter-exit state for multiple things that might intersect a trigger. If you look in the main physics samples, you actually will find such a solution in the events scripts stateful directory. In the next sample, called Stickman Drop, we have these two Stickman figures held together by joints, and the green one on the left, the joints are breakable, so it falls apart when it hits the ground, but the one on the right, the red one, stays intact. If we look at the Stickman prefab, you'll see that the head, arms, and legs all have this fixed joint component which references the torso. The torso itself, meanwhile, is just a regular rigid body. If we look at the two instances of this prefab, you can see that the components of the red Stickman, the unbreakable one, has brake force and brake torque of infinity, whereas for the green Stickman, these are set to 0.05. Now, when you use PhysX, the game object-based physics engine, when these brake force and brake torque thresholds on the joint are exceeded, the joint is automatically destroyed. But in Unity physics, that doesn't happen. Instead, what happens is that Unity physics generates an impulse event, which you then can access in your code and destroy the joint if you so choose. So we have here this Stickman system, which again is updating in the After Physics system group. And in the update, we once again get the simulation singleton as simulation, complete the jobs, so we have safe access on the main thread, and we are looping here over the impulse events of the simulation. And for each event, we record a destroy entity command into our entity command buffer, which we then play back after the loop. Now, actually for these impulse events, unlike the collision and trigger events, is they get generated effectively twice, once for each body connected to the joint. And so in our logic here, we'll end up calling destroy entity for the same entity twice in the same entity command buffer. But that's actually not a problem because redundant destroy commands in a single ECB just get ignored. And lastly, to make what's happening here clear, if we look in the entities hierarchy, you'll see that for each of the pieces that have a joint, they have a child entity which represents the actual joint itself. You can see here the two key components, physics joint, which describes the property of the joint itself, and physics constrained body pair, which specifies which two entities are connected by the joint, in this case, the leg and the torso. Also understand that this parent relationship is really not necessary. It has no implication for how the joint works. The joint might as well just be a totally independent entity rather than a child of either of the entities that it connects. In the last sample, called Blender, we have these two blenders with rotating blades knocking around these little boxes. But in the blender on the right, it is filled with water, and the boxes, while they're in the water, have some buoyancy. They are being forced up towards the surface of the water, but when they leave the surface of the water, when they get ejected out of the water, they lose their buoyancy. This rotate blade system is what makes the blades rotate. The blades are kinematics, so all we need to do is set their angular velocity to this value from the blade component. In fact, because a kinematic won't be slowed down by anything it collides with, there's actually really no reason here why we are setting this every frame. If we just set it one time, they would keep spinning. This buoyancy system here is responsible for applying an impulse force on the floating cubes, the cubes in the water. It also applies this drag effect by diminishing the linear velocity a bit. And notice that the query here is operating only on the cubes which have the buoyancy component. So what we need to do then in this buoyancy zone system is make sure that the buoyancy component is only enabled for the cubes which are currently in the water, which is a trigger zone. So first thing we do in the update here is disable the buoyancy for all of the cubes, and then we get the trigger events, just like we saw in the prior sample. We determine which of entity A and which of entity B is the buoyancy and which is the buoyancy zone. And then for each cube here, we are effectively copying the buoyancy information from the zone to the cube itself, to its buoyancy, and then enabling its buoyancy. Now in this sample, of course, we only have just the one water zone, and so we could just have a global with the buoyancy information. We don't really need to copy it to the individual cubes. But if you imagine we had multiple buoyancy zones with different properties, then the cubes inside different buoyancy zones would need different values, and so that's why we are copying it to the individual cubes. Also, it is a bit wasteful that we are repeating this work for the cubes while they remain inside the water. In principle, we should only really have to do it when they enter the water. And so potentially what we could do is we could, like in the prior sample, we could have enter and exit detection logic, and then only for the cubes in the enter state would we have to do this business here.